Hi, everyone. It's great to see you all here. I'm Christine Kelly, and as the current MAA Director of Project Next, it's my honor to introduce the speaker for the 2025 MAA Lecture on Teaching and Learning, Dr. Eric Hsu. Eric Hsu is Professor and Chair of the Department of Mathematics at San Francisco State University and the Director for Science of the Center for Science and Math, and the Director of the Center for Science and Math Education. He's a national leader in education and education reform at all levels. He's led numerous STEM education projects, including serving as PI and co-PI on 2 NSF grants aimed at broadening participation in computer science, co-PI on the Western Regional Noise Alliance and on 2 NSF Noise grants, and campus PI on 3 regional partnerships with community colleges, specifically the Bay Area Math Collaborative, Silicon Valley Engineering Technical Pathways, and San Francisco Bay Area Basic Skills Consortium. He received an NSF Career Award in 2003 for his work in college math teaching. Dr. Hsu has also led 4 California math science partnerships with San Francisco Unified and San Rafael City Schools. He was also a case study team leader for a large-scale national study of calculus teaching with the Mathematical Association of America. Eric Hsu has and continues to make a tremendous impact in education at all levels. I'm very excited to hear his talk today. Please welcome Dr. Eric Hsu.
Thank you, and thanks for that great introduction. You made me sound so great and old. So this is a synopsis of the talk in case you have to leave at 11. Precalculus was created in a chaotic historical process. Currently, college precalculus isn't that helpful and drives students out of STEM. And how do we decide who's allowed to take calculus anyway? It's hard to create effective placement tests and policies. And finally, I want to tell you about our directed self-placement experiment. Now you can go and catch up on YouTube. Oh yeah, applause. So let's start our story in the 1800s. So in the early 1800s, calculus was not yet part of the regular US college curriculum. But by the second half of the 1800s, the typical college curriculum included algebra and geometry, then algebra and trigonometry, and then analytic geometry. And if you were speedy, there'd be calculus, or in the 4th year, you would take calculus. And to me, it's striking how superficially similar that is to a modern high school curriculum, at least the names. So when US college calculus began, pre-calculus was algebra, geometry, trigonometry, because those were the courses you could have expected advanced students to take. And times have changed. At that time, those courses were different. So for instance, nowadays, if you want to have any hope of following a calculus class from the beginning, you have to know what a function is, you have to know what function notation is, you have to know what Cartesian coordinates are. But it was different back then. Back then, you needed to really understand Euclidean geometry to understand what was going on in calculus. Times have changed. So for instance, let's look at a late 1800s calculus textbook. And by this time, the calculus class had started to look roughly similar to things that happen in our modern calculus classes. You've got limits, you've got rules of finding derivatives, higher order derivatives, power series, partial differentiation. But after those preliminaries, then part 2 is called applications to plane curves. And so all the applications are in terms of geometry and optics. And you could find other applications in there, but the whole thing is framed as, look at how cool this is for solving geometric problems. And to give you another idea of how much geometry was a foundation for thinking, here's another textbook from the time, which is explaining the scary new notions of function and variable quantity and constant. Nowadays, if we wanted to introduce these ideas, you might say, think about the relation between the position of a ball and time, or maybe the amount of money that you have in your bank account for each date, or maybe how many fluffy bunnies there are in each zoo right now. But in this textbook, they said, don't worry about these scary ideas. They're just like the good old equations from conic sections. That won't work as well today. And nowadays, when you introduce a tangent line, you'd probably put it on Cartesian coordinates and talk about secant lines moving around. But back then, the language was extremely geometric. They talked about let PQ be a chord, and let this point Q travel along the curve. And they talk about PQ and PT, and they even attend to the angle QPT and talk about how it vanishes. So just to get in the door, you have to have some understanding of geometry. Trigonometry is also different. So nowadays, you can probably, you still need trigonometry for things like definitions of trig functions and some applications, but if you really wanted to, you could run a version of calculus that doesn't include trigonometry. But back then, trigonometry was the whole foundation for student reasoning about limits, power series, and logarithms. So back then, plain trigonometry text would talk a lot about constructing trig tables. And in order to construct trig tables, you need a lot of limits, series, you need to interpolate values, you need to estimate error. All these things came up all the time. Here's a part of the textbook that derives certain series. This is plain trigonometry. And you might recognize that cosine A formula at the top and that sine A formula. I'll give you a hint. That funny 4 in a box and 6 in a box is just their old way of writing factorial. So these are Taylor series. And so they were using de Moivre's theorem to derive the power series for sine and cosine. So this is the kind of stuff you could expect to learn in trigonometry and then rely on in calculus. And logarithms came up all the time. So in this book, the same plain trigonometry class textbook, they say, as is usual to introduce in works of trigonometry, here's a whole chapter about exponential and logarithmic functions in series. Not only did you have tables of trig function values, but you'd also have logarithmic trig function values. That was really high tech at that time. This book here is bragging in the last paragraph there. The great advantage which we obtain from these logarithmic tables is that the calculations are much abbreviated. You can imagine if you're calculating everything by hand, would you rather raise a number to the 8th power, or would you rather multiply 8 times some kind of logarithm? So this was high tech at the time. But times have changed. So trigonometry stopped covering logarithms and limits and power series, probably because the tables became decreasingly relevant over time. Analytic geometry lost a lot of its topics. Calculus became function-based and not geometry-based. And then, as a side note, even algebra drifted because it was a contested ground for what counts as high school graduation and what counts as college entrance. And so topics like factoring got added in the 1800s because they were easily tested. So times have changed. And as I mentioned, power series reasoning was a continuing thread throughout all these classes back in the day. They used to reason all the time with power series before calculus. Nowadays, we pushed almost all of that late into calculus too. So, but back in the day, even Lagrange and Cauchy wanted to base calculus on the foundation of power series. And in one of the texts I just showed you, the Edwards text, when they define what a derivative is, you can maybe see that limit in the second line. It looks kind of familiar, right? That's a derivative. They title the whole chapter differential coefficient, and they call it a differential coefficient throughout the book because it's a coefficient in a power series. So this was an important thread of thinking back then. So how did these courses change? It happened chaotically. So in 1892, this committee of 10 famously standardized high school courses in the United States, and they put algebra, geometry, algebra 2, trig in the curriculum. And then these courses were often developed district by district or maybe school by school. And if you've been there, then you You probably know that they were certainly underpaid, and there's probably some kind of crisis like, you've got to get this done next year or next semester. And the pre-calculus curriculum, it had to respond to changing educational movements just like every other class, but there were relatively few guidelines, and there was amazingly little central oversight in California, and probably elsewhere. I'm saying California because I'm teaching in California, and there's more documentation about what happened in California in front of me. So the California 68 Strands Report only gives topics up through grade 8. The 72 Second Strands Report, also up to grade 8. The 75 Math Framework, only up to grade 8. Even the 1992 California Math Framework, they mostly say nothing about pre-calculus. They say, preparation for the calculus course, the MAA and NCTM recommend that students who enroll in a calculus course should have demonstrated mastery of algebra, geometry, trigonometry, and coordinate geometry. That's not a lot. That's not a lot of detail, considering this is a 200-page manifesto that called for a complete reform in the way math teaching happened in schools, and had massive a call for integrated high school math classes. Considering it was so opinionated and it triggered off the math wars, which I cannot begin to summarize, this is really saying almost nothing about pre-calculus. And also notice they don't use the word pre-calculus. The word pre-calculus only came into very common usage in referring to courses in the 90s. And then the 1997 California Math Standards. This is the counter-reform. They just punt completely on pre-calculus. They just say, we provided standards for Algebra 1, Geometry, Algebra 2, Trigonometry, but, the last sentence here, schools have different ways of combining the subject matter. Many schools combine some trig, mathematical analysis, and linear algebra to form a pre-calculus course. Some districts prefer putting trig with Algebra 2. So they just kind of wave their hands. We're trying to micromanage a whole bunch of things, but pre-calculus, we're going to let you figure it out. Even the 2010 Common Core State Standards, which is the détente in the war, they don't mention the word pre-calculus. The closest they come is that they call out certain topics as being for students who are going to take advanced courses, such as calculus, advanced statistics, or discrete mathematics. Those are 3 totally different classes. So this is super vague. And as a side note, because of the new math and the creation of AP Calculus, that pushed calculus itself into the high school curriculum, which left even less time to cover pre-calculus material. So it was a mess. What happens in high school also influences college. The high school pre-calculus curriculum and the college pre-calculus curriculum now sometimes share textbook content. The publisher might repackage it somewhat for different markets, but there's often overlap. What happens in high school also anchors what you can expect incoming calculus students to know. And then college faculty who were trained in the United States, they took pre-calculus, and they find it very natural that, oh, this is just the natural prerequisite to calculus, and this must have been done through some rational process. So colleges do try to establish independent standards via entrance and placement exams, and then also enforcing their own pre-calculus courses, but these are highly problematic. So most colleges offer a traditional lecture-based pre-calculus course that has family resemblance to all the other ones. There's usually exponentials, logarithmic functions, trig functions, and then some other random topics from algebra, geometry, and trigonometry. And if you look at what happens to the students who take pre-calculus, it's a bit of a worry. So one study here from Texas Tech, for instance, showed that students who got a B or higher in pre-calculus, 1/3 of them did not go on to take Calc 1. These are students who are supposed to be the winners of this process. From Arizona State, engineering majors who got a C or higher in pre-calculus, 38% of them didn't enroll in Calculus 1. And then if you look at the physical science majors, 55% of them didn't go to Calculus 1. 56% of the math majors, 65% of the life science majors didn't enroll in Calculus 1. And there are a number of other similar studies. And the students who are placed into precalculus are disproportionately women, Black, and Latinx. So you could also try to think about what happens if you control for student aptitude or preparation. So this big Sonnet and Sadler study grouped students by high school prep, which is computed by looking at the courses taken and grades earned and SAT scores and AP, things like that. And so the students who are in the low prep class are supposedly in the similar aptitude preparation. And if you looked at those, the ones who took pre-calculus, their Calculus 1 grades were only 1% better than the ones who went straight to calculus. And then if you look at the high prep group, so this is students who have above average amounts of high school prep and aptitude, whatever word you want to use, their grades actually went down. If you took pre-calculus, then your grades in Calc 1 were 6% worse than if you started directly in calculus. This is really reminiscent of this groundbreaking study, Bailey, Zhang, and Cho, which was a massive study of community college students placed in remedial math. And the students who took remediation had a 79% pass rate in their first college credit math course, which I think is pretty good. So that feels like a triumph, because if you look at the students who chose not to remediate and they went direct to the gatekeeper, only 72% of them passed. So at least in this study, there was a positive effect if you survived the remediation process. But the problem is that a lot of people did not survive the remediation process. And if you also include the people who dropped out, the effective pass rate was only 27%. And one really, to me, very sad statistic is that 11% of that student body, they did enroll in remediation classes, and they passed. They never failed the class, and they still left before they took college-level math. So we are really losing students who seem like they could do it. And if you try to imagine, why would you leave if you're not failing? You can imagine, like, I want to be a scientist, but in order to be a scientist, I have to take driving school for 2 semesters. And they're really hardcore road driving tests that are really stressful. I mean, if you've ever taken driving school, it's stressful. Even if you can get an A, you probably are going to be considering other options. And if you happen to be one of those people who loves driving school or you've never gotten a ticket, just imagine doing 2 full semesters of FERPA trainings. And if you're one of the people who've never done either one of those, then God bless you, you sweet summer child. So that study was about remedial math, but attrition also happens in calculus. So there's a recent blockbuster report by the RP Group, a big study of California community college students, and they looked at STEM majors who really need to take Calc 1. And they want to look at what percentage of them pass Calc 1 within 2 years. And they disaggregated the data by looking at students' highest math class passed and where they started. So, for instance, if you were a student and you passed high school trig or pre-calculus, and you started in STEM Calc 1, then you had a 73% chance of finishing Calc 1 within 2 years. That's pretty good. I don't know if you think that's good. But if you were a high school student, if you passed high school trigonometry or pre-calculus, and you started in pre-calculus, then you only had a 44% chance of getting through Calc 1 within 2 years. So there's a lot of friction in the process. Attrition is real. And then that raises the question anyway, who should be required to take pre-calculus? So a very, very common idea in math departments is to say, look, all these students are failing my class. We should identify who these students are in advance and then have them take a prep class. This is a super common way of reasoning. And that's part of the reason that the entry-level math exam was created. The California State University students, the entire state, 23 campuses, all the students had to pass the ELM, the ELM, in order to take college math. There actually were exemptions, but anyway, for the most part, you have to pass the ELM. And if you did not pass the ELM, then you could not take college-level math, and you had to take some number of prerequisite courses. And that could include Algebra 1, Algebra 2, Plane Geometry, Geometry, College Algebra, Precalculus. And even in today's CSU system, Pamela Birdman's study recently showed that some colleges are still requiring up to 4 semesters of precalculus, of prerequisites. That's a lot of FERPA trainings. Also, if you cross-check what different tests of College Ready show, if you look at, for instance, students who have an SAT math score of 550, so that's actually a CSU standard, those students had an 82% chance of passing the ELM. So there's definitely correlation. But that also means that 18% of the students who are supposedly college ready would have failed the ELM. And then if you look at the students who failed the SAT standard, so they got below a 550, 28% of those students actually passed the ELM. So there's a lot of uncertainty here. The ACT math is another standard. If you got a score of 23, which is the CSU standard, 71% of those students passed ELM. So there's correlation. But that means 29% of the students would have been failed by ELM. And then if you survey instructors directly what they think about the students who are placed into remedial courses, 12.7% of them in this one study said these students are clearly placed too low. So there's just a lot of fuzz in this process, and you're losing students who could potentially do it. The ACT cutoff is set, of 23 was set because according to their models, students have a 50% chance of getting an A or B in college math and a 75% chance of getting a C, which, I don't know, sounds kind of reasonable. But if you use those same models, you can calculate that the students who fail the ACT, so they get less than a 23, 8% of them would have gotten an A in college math. 27% of them would have gotten a B or higher in college math. 52% of them would have gotten a C or higher in college math. So considering that these students are considered not college ready, if half of them would have passed a college math class, at least to my conscience, that's a really big number. And I'm not saying that the ACT is a bad test. This is doing what it's supposed to. They say clearly what it does, and these tests work great if your priority is keeping students out of these classes. Now you might say, what if we combine the measures? That actually does seem to help in studies, but you still have a problem because you need some kind of cutoff. And the problem is that the cutoff is not a step function, not a big step function. So it's not like if you get an ACT 23 score, you have a 75% chance of passing, but if you get a 22, you have a 10% chance of passing. It doesn't work that way. The curve is not that steep around the cutoffs. So you just have a problem with any kind of pre-test cut score model, where if you set the cut score really high, then you lose a lot of students who could have succeeded. And if you set the cut score low, so you save those students, then you don't have much predictive value of student success from the test. Now, some people also say, let's just write our own test. You know what's in your math class. Write a pretest. So SF State, we did that. Many places do. And it's more challenging than it seems. There are entire fields of study, psychometrics, classical test theory, item response theory, about how hard it is to do this. So from 2014 to 2017, I was on the test development committee for the ELM, despite all the bad things I just said about it. The ELM was administrated by ETS, who you might know from television, administrating the SAT, AP, GRE. And we had this panel of experienced professors who would submit multiple choice problems that addressed all the different standards, and then they would go and test them on students in the field, thousands of students. And your problem would get rejected if your statistics were bad. And that happened to me, and it happened to everybody. So what kind of statistics could be bad? So the delta could be bad. So you want to make sure that your test difficulty is consistent across different sessions. And if the problem is too hard or too easy, then it doesn't help distinguish students in the middle. There's this thing called the R by serial, where you check whether higher performing students on the test are more likely to answer your item correctly. Now, when I first saw that, I thought that was weird. I thought, isn't that kind of circular? Doesn't it feel weird that, like, maybe that question gave you information because, like, it would have been biased otherwise? Anyway, I had a lot of qualms with this. But if you stop and think about it, let's say you have a final exam in your class, and the students that got an A in your class at the end, they all bombed question 1. And then all the students who got a D in your class aced question 1. You'd probably start to think, I wonder if there's something up with the question. So that's what this R by serial means. And then the diff, the differential item functioning, they look at students and they try to match the ability in some way, and then they look whether there's different performance between different genders or different ethnicities. And then also, you have to pick out these distractors, and if some of the distractors are really successful, then that's bad, because we're not trying to trick students, we're trying to find out what they know. So there are all kinds of ways to get your problem rejected. It happens all the time. And so to me, the lesson was, it's really easy for experienced professors to write problems that just have unintended behavior, and that you literally could not use on a serious measure of student performance. And so that makes me really concerned about people in math departments with goodwill and good intelligence winging it and just home-growing their own pre-tests, especially since no one's going to give them the resources to validate the test. Usually, you show it to your colleagues and say, what is this? How does it look? Well, it looks all right. How about a question on this? All right, I'm going to skip this for time because I want to talk about directed self-placement. So before fall 2021, incoming first-year students to SF State, and actually to the entire California State University system, were placed into college-ready and need support categories. And the placement was done by the chancellor's office, and they used a specific multiple measures formula that included measures that you might have seen, like SAT math greater than or equal to 550, ACT greater than or equal to 23, and a couple of other measures. And at SF State, if you were deemed need support, then you were required to take a 2-semester version of pre-calculus before taking calculus. So now in fall 2021, the pandemic had messed up the SAT and the ACTs. So that was in 2020. It was hard for a lot of students to actually take the tests. And so that meant that a lot of students who otherwise would have passed the SAT or ACT, they didn't have a chance to do it. So we're going to get a lot of students who were incorrectly marked as need support. And so with a crisis like that, it just seemed like a good time to try it. We're going to try to let the students decide themselves what class to take. So this is directed self-placement, DSP. And also quietly, there used to be restrictions saying that if you were deemed need support, then you were not allowed to take Calculus 1, even if you met the prerequisites, and we ditched that quietly. And so even though I pushed this change, I was concerned because there were strong incentives for students to take the 1-semester pre-calculus, 4 units, instead of a 2-semester stretch pre-calculus, which is 3 plus 3 units. You save time in your degree. It costs money if you're staying longer. And that's just a lot of units to be spending on math, just time-wise. So there are a lot of incentives for students to say, heck with it. I think I can make it, and to overrate themselves, and they're going to put themselves into unsupported courses, and they're going to fail. This is, I would say, the predominant worry people have about directed self-placement. And then that's going to hurt their progress, and then the class will be depressed because everyone's failing, and then the class is going to be harder to teach, and there'll be all kinds of chaos. But you get some good things, too. In theory, students have agency. No one's forcing them to take support classes now. They're the ones who decided it was better for them. No one's telling them you're an inferior student. Instead, it's like, these are the options open to you. What's best for you? They get self-determination. And it's kind of a bummer teaching students who are forced to be in a class they don't want to teach. So morale in a class could go up. And in general, ideologically, you're getting into a tricky situation when you're positioning the institution as always being the gatekeeper, always being the police. So, as I already mentioned, placement tests are inaccurate, and they hold back students who would have succeeded. And students who place themselves are definitely going to sometimes get it wrong, right? For sure. But as a whole, as a policy, this will be worth it if they can just place themselves better than these other placement processes. And another thing is that you're always thinking, well, the students got a 550 SAT, but did they luck out, or was that really low for them? Students know these things. They know what context their grades came in. They know if they pulled an all-nighter partying before the test because they didn't care. And then also another reason that we went for it is that it had been done in other places, self-placement. We certainly did not invent this. Okay, so what we did is we had the incoming first-year students take an online advising module, and they placed themselves into fall 2021. And we gave them a recommendation, and then they were allowed to override the recommendation. We said, you know yourself better, so we recommend that you take stretch pre-calculus 2 semesters, but if you want, you can override it. And then, after they overrode the recommendation, they could just sign up for whatever class they wanted. So they could take 1 semester or 2 semesters. And in the process of the advising module, they did have to acknowledge that the chancellor's office had decided they needed support and ready, that kind of thing. I don't have time to go into it, but I will say that I think my heart was in the right place. I'm the one who wrote the advising module. I didn't know what I was doing. But I think my heart was in the right place because I did some research and looked at a lot of other self-placement tests, and most of them are just testing the student, trying to figure out how good you are at math. So they make you do a lot of math, and then they say, oh, you know what, you actually stink as a math student, which is just a really bad version of all these other bigger tests. So I looked at some literature looking at how students actually make their decisions when they were in other directed self-placement processes. And I didn't try to guess how good they were. I just tried to set out what the support choices were and said, how do you feel when you, actually I can't remember all the questions, but like, how do you respond to frustration in the class? Do you like talking to other students? That kind of thing. All right, so you can't talk about this without getting right to the point, which is how did fail rates change after directed self-placement went in? So, and I'm gonna let you think about this yourself. So before, support students had to take 2 semester pre-calculus. Now any student can take 1 or 2 semesters. And this is the historical pattern of the fail rate in pre-calculus each semester. So my own reasoning is that a lot of the support students are gonna fast place themselves to 1 semester because there's so many good incentives to do that. And so the fail rate will definitely go up. But if I'm lucky, it won't go up past 30%. Because if it goes up past 30%, there's some danger I might get fired. And then that would stop us from continuing directed self-placement. Actually, if you've been a chair, then you know it's actually not much of a threat to say you're fired. If someone says, you can't be chair anymore, I would say, I'll pack up tomorrow. Okay, so you've had a chance to think about what the number is going to be, and the number was 21%. So there's 21%. Yeah, okay, so this is a clap moment, maybe. This is a triumphant moment. But I'm actually a little bit skeptical about fail rates as a way of measuring what's going on in classrooms. But I wasn't going to get fired, and we were allowed to continue directed self-placement. And if you want to see what happened in other semesters afterwards, 27%, not great, but below the 30% death line, 18%. And then I just looked up the data a couple days ago from fall 2024, and the fail rates were something like 17%, but they're not official. So As far as the chancellor's office is concerned, this is a happy ending. And as far as the upper administration at my college is concerned, this is a happy ending, and you should now leave the talk. Okay, so now that they've had a chance to leave, let's talk about really interesting things. Because it's actually quite hard to interpret fail rates. So ever since the pandemic and post-pandemic, each semester has been completely different. You have small classes, then you have students coming back to in-person teaching, and then you have the effect of Chegg and other cheating sites, and then you have ChatGPT. Like, if you really investigate carefully, it's quite subtle to interpret these fail rates. But I think it's safe to say that self-placement has been fine. It wasn't a riot, and signs are positive, cautiously saying. So there's some other interesting things that I did want to share that I feel more confident about. So now you get to play chair without all the people complaining to you all the time. And you get to predict the enrollment change. So remember, this is a chart of students who are taking pre-calculus. And in fall 2020, before the change, 56% of them took one semester pre-calculus. And 44%, naturally, took the other one, stretch first semester. So now that everyone can take one semester pre-calculus, what percentage of students do you think will opt to take one semester pre-calculus? So you should actually think about this. And I'll give you a hint. Here's the answer I had to come up with. You might say, I have no way to come up with this number. This is just a total guess. And that was also my situation. When I was a chair at the time, I had to decide how many sections to offer of each one of these classes. So like many things you do as a chair, I had to pull these numbers out of my butt. So you get to do the same thing. So those are the numbers I projected. And I pretty simplistically said, well, maybe about half the students in the stretch pre-calculus, half of them are going to go over to the one semester version. So that would put it around 78%. But maybe about 15% of the one semesters want to take it slow, and they're going to go back to the other side. Pretty clever. So I got 68%. Any opinions about this? Maybe I can take a poll. Could you raise your hand if you think that the number of students who opt for pre-calculus one semester, the short pre-calculus, is bigger than 68%? Okay, 20% of you. How many of you think it was less than 68%, like 56%, between 56% and 68%? Okay, and then the rest of you are miscellaneous or on your phones. All right, well, if you guessed lower, you were correct. So the number of pre-calculus students who opted into pre-calculus actually went down. I was scrambling to change a bunch of these one semester pre-calculuses back into stretch pre-calculus. Only 43% of the students ended up opting for one semester pre-calc. Now, where did I go wrong? Where did most of us go wrong? Well, here was my projection. These are percentage of students choosing one semester. And so in the old days, there's no choice. So if you were a need support student, there's 0% of you chose one semester because you had no choice. College ready, all of you had to choose one semester pre-calculus. And I decided, with my brilliant modeling, that half of the need support students would pick one semester, and 85% of the one semester students would stay there, but 15% would move down. And that's not what happened. What happened was that the need support students, only 32% of them picked one semester, which is a lot lower than I was expecting. And I really, really, really was not expecting only 59% of the college-ready students to pick one semester pre-calc. That was shockingly low to me. And this is a phenomenon that was not just one semester. Fall 22, if you look at the need support students, 39% of them opted for one semester. 54% is a bit higher in that semester, but fall 2024, only 42% of them opted for one semester. And then college ready, it was similar, 59% in 21, and in 22, only 56% of the college-ready students opted for one semester pre-calc. And to me, that was too low. I know I just gave you a whole spiel about how you have to trust students and that they need self-determination, but it's one of these things that's like, have self-determination, but not like that. So I don't know if I was right or wrong, but given all the stuff we looked at about how much attrition there is, if you just take 2 classes, you're really putting yourself into jeopardy. And I really did not want people to do that unless there's a good reason to do that. So I just forbade college-ready students from taking 2-semester stretch pre-calculus. So, I mean, there's no choice there. Actually, the choice is that it should be 100%, right? That in fall 2023, the college-ready students should 100% be taking 1 semester. But there's ways around it. Students could get permission numbers from instructors and fiddle with the computer. But I was concerned about attrition, and I was also concerned about students from minoritized groups who have lower overall confidence, possibly. Maybe they're slow placing themselves. All right, let's see. How much time do we have? I have 15 minutes? Oh, that's great. I'm ahead of time. I can talk real slow. Here's another prediction question for you. So let's look at elementary statistics. Now, before fall 21, if you were in elementary statistics and you were in needs support, you had to take a 2-unit co-requisite. Okay, you had to take a 2-unit co-requisite. In fall 21, because it was such a weird semester, I gave people a choice that they could take a large elementary statistics section without a co-requisite, or if you want one of the small ones, then you have to take a co-requisite. So the small sections were meant for students who thought they needed extra support. So those numbers stayed pretty stable. In fall 19, 26% took the co-requisite, 26%, 21, where I kind of passive-aggressively coerced them into taking co-requisites by bribing them with the small sections, is 27%. But then in 22, we left a completely free choice. So if students are given complete free choice taking elementary statistics at SF State, how many percent of them do you think would opt into the co-requisite? You should think about this. Well, my guess was about 1/3 of the students who were taking it would stop. And so 18% of the students. So that was my guess. I'm not going to poll you all because you all did so much better than me on the last one. But the actual answer was, in 2022, 8% opted into it. And then the next semester is below 1%. Students don't like co-requisites at SF State. Part of it is probably that you have to go and find them. You have to specially enroll in the co-requisite. So I'm sure that's part of the problem. But even if you advertise it really heavily and have people announce it, 2 more units of elementary statistics is just a big ask for a lot of students. That makes 5 units of statistics in a semester, especially in your first year in college. It also didn't help that some of the advising people on campus told the students the same thing. They said, oh, 5 units is a lot, and didn't really explain the support aspect of the 2 units. Okay, so I think I'll wrap up with this other comment. So you remember that we gave students a choice. So students took this advising module, and then they were, we said, oh, you should take support, or you should take non-support. And then they had a chance to override it and say, no, I disagree. And so then they registered the overrided recommendation. And they overrided about 30% to 50% of the non-support recommendations, depending on the class, and about 10% to 20% of the support recommendations. But then they wouldn't follow their own recommendations. So they would just go and enroll in whatever class they felt like in the end. And it probably was through some very reasonable process where they decided, you know what, I know I said in the module that I should take 2-semester support because it'll be so much better for me. But I really need to get out of here, so I'm going to take the 1-semester class. So I'm not saying it's irrational, but students ended up not following their own recommendations half the time. Okay, so in summary, students with free will, they don't want to fail, so they will choose supported math more than you think. They're not going to necessarily rush to take the fastest possible, most advanced pathways. But even though they like support, if that means a lot more math units per semester, at least on my campus, they don't want it. That's too many units. So co-requisites are not attractive, and I got to find some way to encourage them in a different way. Students freely ignore recommendations, and overall the passing rates are pretty similar to before directed self-placement, so I think it's working adequately, even though there's a lot of things that we have to investigate. So in conclusion, I really think the research shows that you should not force students to repeat precalculus. There's a whole section about how students do depending on their starting class. A lot of students who hit college have already had precalculus. A lot of them had calculus. I don't have time, but if you go back to that table I showed, there are students who passed calculus in high school, and then they're getting started off in algebra 2. That is so demoralizing. I might quit science just on principle if you did that to me. So also, to me, I would say don't force students to take more than one prerequisite course. Algebra, geometry, trigonometry once meant a lot to calculus, but over time, it's drifted, so there's just not as much direct application. Placement tests are very troubled. Self-placement works okay, but I really need to research how it's affecting women and minorities. If you want students to take a co-requisite, then you better have some strong incentives attached or somehow coerce them. And as a field overall, we have to keep experimenting to improve precalculus. And if you want to do that, you need to build on other people's work and remember to measure complete student retention, not just the success in each individual class. And now homework for you. If your conscience has been pricked and you want to do more, you need to dig up your own local evidence to see what's happening on your campus. Whenever people have math reform, people always say, that won't work on my campus, it's different for my students. Maybe it is, so find the evidence. And if you decide to remake your curriculum, build on existing work. I have a couple of links if they're not links, they're papers. Papers if you're interested in learning more about research in undergraduate math education. There's a whole special interest group in the MAA. And I guess that's the end.